So in this video, we're going to start extending our theorems about discrete time martingales to the continuous time setting. And the first theorem we are about to consider is the theorem about stopped martingale. And you remember that in discrete time, it told us that if I have a martingale and a stopping time with respect to the same filtration, and I stop the martingale at that stopping time, the resulting stochastic process is still a martingale. Now we want to do exactly the same thing, but with a martingale indexed by a real number with respect to a filtration also indexed by a real number and a stopping time with respect to that filtration. So this is the statement here, and a martingale, a stopping time, all with respect to that same filtration indexed by the non-negative reals, and the corresponding stopped process is a martingale. So let's see how we prove that. Now, all of these extensions of our discrete time results to continuous times will be about approximating the continuous time by the discrete time and then passing to a limit. Sometimes the passing to a limit will be fairly straightforward. Sometimes it can be pretty tricky. This theorem is a case where it's not straightforward. So let's have a look at how we prove it. So what do we need to show? Right? We need to give ourselves two non-negative real. Let's say that S is the greater one and T is the greater one. And then, T is the greater one usually. So let's do that. T greater or equal to S. And we need to show that the conditional expectation of M T minimum tau given Fs is Ms minimum tau. All right. And so I'm going to do that by an appropriate discretization and limiting process. So think about it this way, I have my interval S to T, and I'm going to split that interval into finitely many subintervals, and I'm going to make this subinterval have lengths 2t minus n for some natural number n. And the idea is that eventually I'm going to send this natural number n to infinity, get these intervals to shrink to a point, and approximate the continuous time by discrete times in this way. Okay, so I want to give names to this point, this discrete set of point in my interval st. I'm going to call that one qn1, say. And so what I want to define is a set of point. Let's call them q and k for all k in n. Defined in that way, so I'm starting at S and I'm adding a multiple of the distance between S and T divided by 2 to the n. So I'm going to do that for k between 0 and 2 to the n. The idea being that, sorry, that's not S minus T, that's T minus S here, that if I take k equal to 0, then I'm at S. And if I take k equal 2 to the n, then I'm at t minus s plus s. So I'm at t. And after that, let's stay at t. So let's also say it's t if k is greater than 2 to the n. Okay, so that gives me a countable, well, a discrete actually set of points, but indexed by all the natural numbers. Okay, now I'm going to define the corresponding discrete filtration, right? So I'm going to call f and k is going to be, by definition, f at point q and k. Right, so f and k is a filtration, and let's start. So that's for all k in n, and you can remark that we have f n 0, that's Fs, and we have Fn k equal to Ft for all k greater or equal to 2 to the n. Right? Now, with respect to that discrete filtration, so if I look at M, Q, and K, and let's call that M and K, just to be consistent with notation, then M and K for K in N is a martingale with respect to the filtration fkn. All of that is indexed by k. N is a fixed parameter that just gives me my level of approximation. So I have a discrete martingale now with respect to discrete filtration, so I can stop that with whatever stopping time I want, as long as I take a stopping time with respect to that discrete filtration. So I also need to discretize my stopping time tau. And well, here's the way we're going to do it. So we're going to keep defining, should have wrote define here. So I've defined my discrete filtration at the scale 2 to the n, my discrete martingale at the scale 2 to the minus n. I'm defining my stopping time at that scale, let's call it 2n, to be the minimum of those k's between 0 and 2 to the n, for which q and k is just above t minimum tau, right? So I want it to be as close as possible. I want that tau n to be as close as possible to tau, or sorry, qn of tau n. That's the idea. I should write it up. The idea is that qn of tau n should tend to tau in some sense. So I'm going to put quotation marks. I'm not telling you in which sense it tends to tau for now, but the idea is that I'm approximating tau, right? I'm picking in that discretization of the interval that I just drew a minute ago. You know, if tau, let's use a different color, if tau is somewhere here, say, then I'm going to pick, this is going to be qn of tau n, and the first point in my filter, in my discretization, that is just above that tau. Okay, and the idea is, well, if I send n to infinity, the gap between the actual value of tau and the value of qn of tau n is going to get smaller and smaller. Okay, now let us show that tau n is indeed a stopping time with respect to the discretized filtration. Stopping time with respect to fkn. Okay, so how do we do this? We give ourselves a k in n, and we need to consider the set where tau n is greater than k. And we need to show, or its complement, tau n smaller or equal to k. That's the same thing, right? If I show that tau n greater than k is in fkn, then its complement is going to be in fkn, because fkn is a sigma algebra. So this is, if tau n is greater than k, then, okay, then that means that the first value of qn tau n above tau is past the point q and k, so t minimum tau would have to be greater than qn of k. Okay, but notice that t cannot be greater than qn of k, right? Qn of k is something between s and t. So this is really the same thing as saying that tau has to be greater than qn of k. But now, because tau is a stopping time with respect to the continuous time filtration, this has to be in f of qn of k. Right, since tau is a stopping time with respect to the filtration ft, so I can apply that for the choice of t being qn of k. Okay, and that's exactly by definition fkn. So what have I got? I've got that tau n, say, smaller or equal to k, which is the complement of this set, is in fkn for all k. So tau n is a stopping time with respect to the filtration fkn. Right, so now I can apply the stopping time theorem for discrete time martingale. So by the discrete time stopped martingale theorem, what do I get? I get that the expectation of m of qn of tau n given fs, well, that's the expectation of m of qn of tau n given f0 of n, but and m qn of tau n is what is exactly it's exactly mn of the minimum of, say, tau n and tau n. All right, and condition on f naught. But if I condition on f naught, and because my discrete time martingale is a martingale, I get m0 n. And what is m0 n? Well, it's m of q n of 0, which is m of s. Okay, so conditioning m of qn of tau n on fs, we get ms. So what we need to show now is that qn of tau n does tend to tau, and m of qn tau n tends to m of t. And the corresponding conditional expectation tends to the corresponding conditional expectation. If we prove all of that, then we would get our result. So that's the idea here. The idea is that the expectation of m, qn, tau n, fs, and I'm going to put that between quotation mark because we need to make it precise in which sense we're taking the limit, will tend to the expectation of m of, so qn of tau n stays below t, so it's going to be the expectation of the minimum of t and tau given fs. And then our proof will be concluded if we can indeed pass to the limit in this equality. Let's see how this approximation works now. So I claim that convergence in L1 will be enough to get our result. Now let's see why that is. First of all, let's remark that we really don't have to do much work to get the result when tau is smaller than s, because if tau happens to be smaller than s, I'm looking at mt minimum tau minus ms minimum tau, and I'm conditioning on fs. Well, if tau is below s, it's also below t, so both of these minimums are actually attained at tau. So what I have here is the expectation when tau is smaller than s of m of tau minus m of tau given fs. So that has to be 0. So there's really nothing to do when tau is smaller than s. Now, when tau is greater than s, what I could do is I could look at this conditional expectation. I need to show that this is 0 almost everywhere, and one way to do it will be to take its absolute value and show that its expectation is 0. And now for this expectation, I can start using some approximation. So first of all, let's notice that this indicator function here is certainly fs measurable because tau is a stopping time. So what I have here is smaller than the, well, it's actually it's equal to start with, the expectation when tau is greater than s of the conditional expectation of mt minimum tau. Let's introduce my stopping time, t minimum qn of tau n, and let's add it back. By the way, qn of tau n is always below t by our definition, so this is redundant anyway. And then minus ms minimum tau, but I'm looking at only a dose omega where tau is greater than s, so the minimum of s and tau has to be s. Right, so I'm just adding 0 here and just rewriting things in a simpler way using the information that I've got. Right, so this is what I need to show is equal to 0. But now I can just use Jensen inequality in all of this, and I can get that this is smaller than the expectation. I can forget that, I can integrate over a bigger set and forget this indicator function. If I show it 0, then I'm showing something even stronger, and I'm gonna have the expectation of the conditional expectation of absolute value of m t minus tau minus m qn of tau n given fs, plus, by triangle inequality, the expectation of the absolute value of the conditional expectation of m qn minus tau n minus m s given fs. Okay, but that second term is 0. That's an absolute value here. That second term is 0 because of the discrete time martingale theorem. So we've already shown that that term is 0. And we have the first term here. It's an expectation of a conditional expectation. Conditioning doesn't change expectation. So what I have here really is the expectation of the absolute value of mt minus minimum tau minus m of qn of tau n. So really, what I need to show is that this goes to 0. So it suffices to show that, well, that this expectation goes to 0, puts in another way that mt minimum tau minus m of qn tau n in L1 norm goes to 0. Right, that's an L1 convergence, and it would give us the result. Now, we've studied uniform integrability precisely for that purpose. It would follow from two things: from a almost sure convergence combined with a uniform integrability. Right, so uniform integrability. Okay, but remember that we've seen that uniform integrability follows from being uniformly in L2, for instance. So this would also follow from proving two things: one, almost sure convergence, and two, uniform L2 boundedness. So the supremum of the expectation of m of qn tau n squared being finite. Okay, so let's prove these two things. Let's start with the almost everywhere convergence. So one follows from continuity, or almost sure continuity of the martingale. Right, we're only looking at a continuous martingale in this theorem. I realize I forgot to put that when I rewrote the statement of the theorem here. It's extremely important, but it is in the note. So I have a continuous martingale, and one's going to follow from the continuity of that martingale, because for every omega in omega, if I look at t minus tau of omega minus qn of tau n of omega, well, qn of tau n of omega is the first number in the interval above tau of omega, and so this here has to be smaller than 2 to the minus n. So of course, for every omega, so it goes to 0 as n goes to infinity. So I am indeed approximating my my stopping time. Now, up to a set of measure 0, the map t goes to mt minimum tau is continuous. So okay, so I should write it like that. There exists a set A in omega, which has probability 1, and such that for every omega in A, such that, yeah, for every omega in A, mt of omega minus ms of omega, let's not use s, mt of omega minus mt prime of omega goes to 0 if the difference t minus t prime goes to 0. So I want to apply that, and well, I can say for every omega in A, mt minimum tau of omega minus m qn of tau n of omega. It doesn't matter that my times are actually dependent on omega. I fix an omega and know the difference between this point of time and this point of time for that fixed omega is smaller than 2 to the minus n. So the distance t minus t prime goes to 0. So this has to go to 0 as n goes to infinity. Right, so for every omega in omega, I have the convergence of this sequence to the limits that I want. And that sets A as probability 1. So 1 holds. Just 1 holds. Okay. Now, to upgrade from this almost sure convergence to a convergence in L1, I want to apply this result that's based on uniform integrability. So I need to prove 2. It just remains to prove 2. Okay, so uniform L2 norms of the MQN of tau n. Let's see how that works. Okay, so I need to control the expectation of M of Qn of tau n squared, and I need to do that for all n and get a bound that's independent of n. Now, Qn of tau n can only take finitely many values. Let's call them k, right? It could be something between 0, tau n could be something between 0 and 2 to the n. Qn of tau n would be something between s and t in this discretized version of the interval. So what you have is this 2 to the n possibilities. Okay, and now I'm claiming that this can take a much simpler form. So first of all, if tau n is k, then this is k. So what is this object here? This object here is equal to, I claim, the expectation when tau n is k of mt given fkn, right? That's by the martingale property, because this expectation of when tau n is k mt fkn, right? Tau n being k is fkn measurable. That's because tau n is a stopping time. So this is the same thing as whenever tau n is k as the conditional expectation of mt given fkn, which is the same thing at m and fqn of k. And so by the martingale property, so this is because you have a stopping time, and this is because you have a martingale, mt, this is m of qn of k. Very good. So really this L2 norm squared that I'm trying to compute is a sum k equals 0 to 2 to the n of a expectation of a conditional expectation when tau n is k of mt given fkn. Right, but a expectation of a conditional expectation, sorry, I forgot to square that. And then once I've squared that, I can use Jansen to get the square inside, because the map x goes to x squared, it's convex. So this gives me the expectation of the conditional expectation of indicator function of tau n being k, mt squared given fkn. And now an expectation of a conditional expectation is just the expectation. So this is equal to the sum k equals 0 to 2 to the n of the expectation when tau n is equal to k of mt squared. But now you can bring the sum back inside by linearity, and this is equal to the expectation of mt squared, because the sum of this indicator function is just equal to 1, because the set Tn of k Tn equal to k are disjoint. So the sum of indicator of tau n being equal to k from k equals 0 to n is always smaller than 1, or actually it's equal to 1 almost surely. Is equal to 1, since the union of the set tau n equal to k is all of omega when k runs between 0 to the n, and the set are disjoint. Okay, so what have we proven? We've proven that the expectation of m of q n tau n squared has to stay smaller than the expectation of mt squared. That's really just a consequence of the fact that whenever I have a martingale and I take a convex function of it, I get a sub-martingale as a consequence of Jensen. And then I take the supremum of that, and that supremum stay bounded, and therefore m of q n tau n as a sequence of random variable is uniformly integrable. And that concludes the proof. Uniform integrability combined with this almost sure convergence we had before give us L1 convergence, and L1 convergence is enough to pass to the limit in the defining equality for being a martingale. Let me show you that bit again, going all the way back to what we're trying to do here, right? We showed that we needed to prove that this quantity was equal to 0, and we realized that it had to be smaller than this L1 norm of the stopped martingale minus its discretized version. So we just needed to show an L1 convergence of the discretized version to the continuous time version, followed from almost sure convergence plus uniform integrability. Almost sure convergence is a consequence of continuity. Now, I cannot stress the importance of that too much. It's very unfortunate that I had forgotten to write it earlier in the statement. Now, this is really about continuous time martingale, and continuity of the martingale will be used throughout all of the proofs we'll see in this chapter, because while we're trying to approximate continuous time by discrete time, and that's going to be very difficult to do if we don't have some continuity in time of the objects we'll look at. But from the continuity, we got the almost sure convergence, and then it was just a matter of getting uniform integrability in order to upgrade from almost sure to L1 convergence, and that followed from an L2 estimate. And that L2 estimate is very generic, right? When we look at martingales, we usually have all the L2 norms of all of the discretized object controlled by the L2 norm of whatever object is at the end of our time interval. Okay, that concludes this proof.